So my name's Eric Evenchick. Today I'll be presenting CANtact Open Tools for Automotive. And today we'll kind of be going through a background of how automotive networking works, sort of a primer, and then talking specifically about the hardware and software tools we're working on, and then finish off with some thoughts on automotive security and where we're going. But first, I'm curious, has anyone here ever connected anything to an automotive CAN bus before? Got a few hands. It's always good to know kind of who has, because it's something that we don't see much experience with in this industry. Up until recently, there wasn't much, and now it's starting to become more and more widespread. And so, automotive security. Traditionally, there's a lot of security by obscurity. They define proprietary layouts of the data on the bus, and they assume that people won't find out what it is. And this held true basically from when CAN was new back in 1989 until about 2010, when the AutoSec researchers at the University of Washington and the University of California, San Diego released sort of the first papers on the topic. Autosec.org, you can still find those, and they're actually great research to get your feet wet with automotive security. And they realized that once they got into CAN, once they could get on the bus, a lot of the stuff became pretty easy. And this assumption that it was hard and that the tools were expensive, it broke down. So once we connect to IP, we see an interesting parallel, which is some recent attacks. There was the Fiat Chrysler one back in August at Black Hat USA, and there we saw an open port that was accessible over the internet on a head unit. And this is something that IT folks are really used to checking for. And with the tools that we have, everything from something as simple as Nmap might be able to identify this type of stuff, it's pretty easy to identify those problems. A more recent one was the Nissan Leaf, and I apologize if there's anyone from Chrysler or Nissan here. I'm not trying to pick on you, it's just two examples. But with the Leaf, they use this API for the app to be able to control certain features of the vehicle. And one thing that you look at whenever you're looking at APIs is how are they doing authentication. The way they did authentication is highlighted here. They used only the vehicle identification number, or VIN, to authenticate and allow the remote control. Now, a VIN number is something that's actually stamped on the front of a car, and there's actually databases where not anybody, but people can look up VINs by who's registered to the vehicle. So clearly that's not a very good authentication token. And so this broke down as well. So once we have these IP things show up where people are very used to dealing with these protocols, it breaks down pretty quickly. Whereas when you look at CAN, 1989 to 2010, there wasn't too much work done on it. So the first thing to do here, and I apologize for those that are automotive folks because I think it's important to do sort of an introduction to CAN and automotive networking. So we'll do this kind of quick. But CAN is Controller Area Network. It's been around since 1989 when Bosch first created the first controllers and transceivers. The reason you see this in the automotive world is that there's low cost and highly integrated controllers. So not only are the CAN controllers quite cheap, they're actually built into the microcontrollers, and these are controllers that meet the required certifications to be used in automotive devices. We need devices that are going to be able to deal with temperature ranges, vibration, temperature cycling, humidity, and there actually are qualifications. The main one is AEC Q100. If that part doesn't have that qualification, you won't really see it in the car. And it just so happens that because CAN has been used in automotive, it's very easy to get parts that have this qualification and that have built-in CAN controllers. Also, there's history. Everyone uses it. There's tools out there. People are very aware of how it works in the automotive world. So there are a number of types of CAN. The main one we'll be talking about is differential or high-speed CAN. This is what you see really between most vehicle controllers that are of importance to vehicle safety and vehicle operation. There also is a low-speed CAN bus, and this is used more for convenience features, things like windows, lights, doors, things that are not as critical to the safety of the vehicle. It's cheaper to run one wire instead of two, so instead of running a differential signal, they just run one wire and ground, which is the chassis of the vehicle, and you can reduce your costs of the transceiver, of the connectors, and of the wiring harnesses. Fault-tolerant CAN is something you see more in the airbag world. It actually has the ability to operate as differential CAN, but in the event that one of the two wires gets cut for some reason, it becomes a single-wire CAN bus, so you end up with some tolerance to faults like breaking wires. And finally, we have CAN-FD, which is a newer technology. It actually gets over some of the limitations of CAN. It's starting to be adopted, and we'll talk a little bit more about that later. But a typical CAN bus that you look at is going to have a collection of controllers that are all sitting on a bus. Now, it's important to note here there is no switch like an Ethernet network. They are all just connected up to that bus. So everyone has the ability to control the bus at any time, and using an arbitration technique, they actually manage to decide who should talk when. And in a lot of systems now you see gateways. This is sort of a naive, really simple, fits on a slide diagram. Real automotive architectures are quite a bit more detailed and complex and are also typically proprietary, so I can't put them on a slide. But this has a BCM, or a body control module, acting as a gateway between two buses. So it will let you get messages or get data from one bus onto another. Example here, you might have an engine control module. That's generating an RPM value. This instrument panel, which is on this other low-speed or single-wire CAN bus, it needs the RPM value to properly display your TAC. So the BCM is going to receive that information, wrap it up into a new CAN frame, and transmit it maybe at a different rate, maybe in a different way, but it'll be transmitting that message. So we're going to look at sort of the software model of how CAN works. I'm not going to get too much into the electrical details of CAN just because it's not terribly relevant for this topic. It's a bit out of scope for this. But whenever you're looking at it as a software person, you have a CAN bus, and this is a collection of controllers that are all networked on this single bus. It was the red and green lines in the previous picture. On the bus, you're going to have frames. And a frame is a single sort of CAN packet. It's an atomic thing that contains three main items. There's an identifier, and that tells you what is the message, so what's going to be inside of it. There's a data length code, which simply says how many bytes are in this message. It's 0 to 8. CAN only supports payloads of up to 8 bytes. Then there's the data part, which is your 0 to 8 bytes of data. And really that's it. It's quite simple. That's all a CAN frame is, and later we'll see CAN frames, and that's all that's inside. If you look at the electrical stuff, there's some CRCs that happen, and there's some acknowledgement that actually allows these things to be quite reliable in practice, but if you're developing for CAN, this is really what you're looking at. So there's two main ways that CAN is used in vehicles, and the first one is the signal databases. If you work in the automotive industry, I'm talking about DBC files is typically what these are represented as. And this is a rather simple example of how this works, but this is how, when your vehicle is running normally in just day-to-day operation, almost all of the communication happens this way. And in this example, we have a CAN frame, and it's leaving the engine control module. It's being picked up by an instrument cluster. Now, I have marked out that these are the controllers here. In real life, you're connected to the bus. You don't actually know who is sending a frame, and you don't know who's receiving it. It's just being published. It's a totally broadcast system. But for this example, we have the engine control module, instrument cluster. We have an ID of OX123, and then some data. Now, when you first connect to a CAN bus, you're going to see data flying around, a lot of these, all over the place. And what's actually happening in your vehicle is decoding. So, it's quite simple. The bytes of this message will have meaning, which is predefined at the time where the vehicle software was designed. So, in this case, these first 2 bytes might be an engine RPM. I actually saw a CAN bus just the other day that it was, in fact, a message, not that ID, but it was the first 2 bytes for an engine RPM, just direct correlation. So this OX5DC, you know it's a 2-byte long message. You can then take that value, convert it to engineering units, and you get something like 1,500 RPM. The goal of a signal database, or the purpose of a signal database, is to tell you what the IDs mean, what's contained in these 8 bytes, because it might be engine RPM, vehicle speed, is it raining, 1 bit of the rain light sensor, headlight status, sunroof status. All these things are being broadcast all the time. So the database tells you what's in there, and also how to convert from just these raw bytes on the bus to actual engineering units, which is really useful whenever you actually want to get real data out of a vehicle. It's not so useful to know that it's OX1234. You want to know that that means that your high voltage battery in an electric vehicle is at 63.27% state of charge. So those conversions are done by these signal databases. They're all defined at the time where you design the system, and then the software that's actually running on the controllers has this statically set up. There's another way that CAN is used, and this is not a day-to-day thing, but it's definitely true of any vehicle you have. Absolutely any vehicle that's passed or was made past 1991 is going to have some form of diagnostics. It was first mandated solely for emissions purposes by the California Air Resources Board, who actually have led a lot of innovation in automotive. And they wanted to be able to get data on vehicles for the purpose of being able to do smog tests, because in order to look at the emissions of a vehicle, know what the vehicle's running, and actually be able to tell what the emissions were, you need certain information on airflow, fuel flow, things like that. So they came up with this OBD, which is really a read-only protocol. It's the only thing you can really write with OBD is you can clear fault codes, but you can read out what are called PIDs or parameter IDs for all sorts of stuff. You can get vehicle speed, engine RPM, airflow values. You can get temperature sensing, all kinds of information. It's all standardized. There's a great Wikipedia article that has every PID. It's basically the #1 reference online for that information. But OBD, that's the limit. You can get fault codes, clear fault codes, that's it. Now, manufacturers, they needed to be able to do more than that for things like setting up vehicle VIN numbers or reflashing vehicle firmware. And there's a number of approaches for this between, when this all started up until around 2008. Around 2008, everyone started to standardize on Unified Diagnostic Services, or UDS. And UDS is a diagnostics implementation. It's an application-level implementation that provides different services for everything from updating firmware to writing arbitrary memory if you wish to implement that. And it's based on a request-response paradigm. So you send a request out to an automotive controller, and most automotive controllers in a vehicle will have this implemented, asking for, read this identifier, which might be some arbitrary data. I want to do a firmware update. I want to read a particular memory address. I want to reset this ECU. There's about 20 or 30 of the different services that you can actually pull off. And that controller, it's going to determine if it's happy, if it's going to let you do the thing that you requested, and if so, it's going to send you back a response. So you typically see this as a scan tool, which is what a mechanic is going to be using plugged into your vehicle over the OBD port in the car. It's going to send out a request. That server, which is the actual controller, generates a response and sends it back. And you can chain these together to create sessions. And there's different ways of implementing security for the sessions and all that, but this is the other common application of CAN other than just signal databases. So if you want to do this stuff, you're going to need some tools, because MacBooks and Lenovo's or whatever you have on your lap, those don't do CAN. They do Ethernet, they do USB. There are no CAN devices built in. There's a lot of different tools out there, and almost all of them are expensive. So Vector is sort of like the gold standard in the industry. They make very complex tools that are used for all sorts of stuff and are almost completely out of the range of anyone but OEMs or people with a lot of money to spend on research. You're looking at typically 5 figures plus. These are in US dollars. Cavasser is another company. They make much simpler tools. They're quite a bit cheaper but still expensive, and their software is sort of useless for anything but just looking at frames and sending single frames. There's Pcan and Grid Connect, same device, different name. It's about $250. This one is actually great for the price. For a while, it was like the cheap tool you would buy. But their software, the free stuff is really limited. The full software starts at $600, which is decently cheap, but by the time you buy all the add-ons, it gets really expensive, and it doesn't do diagnostic protocols, really. It does some of the heavy-duty trucking ones, but it doesn't do most of the stuff. There's the ECOM cable and CAN capture. That was used by the folks that did the Fiat Chrysler research. It comes with some basic software for around $1,300, but you can also do your own software development around it. But it's a closed source tool. It's not really open. There's an API. It's Windows only. And And the last one I put on here, which is actually a really cool thing if you want to just like mess around with your car a little bit, is the ELM 327, which there's a lot of devices that are branded as ELM 327. They're all based on either the actual ELM 327 chip or a clone, and they are just diagnostic devices. So they can do OBD and they can do some of the more complicated diagnostics. You can buy one of these for like $20. You can plug it into your car. They have Bluetooth ones, which you may or may not wish to put in your vehicle. That's your choice. They also have USB ones, and you can use those to pull your fault codes and see what's wrong with your car, or clear that check engine light. And if you just want to play with this stuff, that's a great way to get started. You'll probably save yourself the $20 the first time you use it. The open source tools. So there have been a number of things, and I like to mention kind of the stuff that's come and why I felt it was necessary to build new tools. The Goodthopter 12, it's part of the GoodFET project, if you're familiar with Travis Goodspeed's stuff. It's actually done by a guy named Andrew Reiter, who built a GoodFET that did CAN. And it was a low-cost tool. The only problem is you can't really buy them. They're not available. You can make the PCB yourself and solder it up on a hot plate. Most people don't want to do that. CAN Bus Triple was an open-source device. It was actually a Kickstarter, I believe. And it was an Arduino-compatible device with 3 CAN buses. Their goal was, hey, you can embed this in your car, and it can connect to CAN. It can connect to some other things as well. It had Bluetooth. And then you can develop your own, applications for whatever you wish to do, maybe data collection or some remote control functionality. So that was the target of that device, and it's kind of a neat little box that you can just throw in a car and use the Arduino tools, which are pretty simple to get started with, to develop for. On the software side, we have Socket CAN. This is a Linux-only thing, but it's kernel support for CAN devices. So you can actually install a kernel module, and if you're on Ubuntu, there is a package, just apt-get install CAN-utils, and you're good to go. And this makes CAN devices look like Ethernet devices, and it lets you program them with BSD sockets. So it's a really easy interface, and it makes the hardware sort of disappear, and you can write anything that supports Socket CAN, you can write just BSD sockets for, which is great. And another awesome part of that is Wireshark actually has support for CAN. Most people haven't played with that. It's unlikely that you have a CAN Ethernet device on your computer. But if you fire up Wireshark and you have one, you can go onto it and it will actually start displaying all the CAN frames. But Linux only, because it needs Socket CAN. And it only displays information similar to Wireshark for IP. You can't really transmit packages. So I went through all this, and it was actually back in late 2014. I gave a talk at TourCon about tools and CAN. And someone who was part of that original group with the University of Washington was like, "You should build a new one." And he bugged me for long enough, so I decided, okay, we'll do it. And decided to launch some new hardware, which is the CANtact device, which is this guy. And this supported Socket CAN on Linux when it was launched back in 2015. So you can just plug this into anything running Linux. Ubuntu is the easiest way because you install one package, you run the slcand daemon, and you suddenly have a CAN device. You can fire up Wireshark, plug it into a car with one of these OBD cables, and you'll start seeing frames, which is pretty good if you know Linux and you're familiar with that. The problem was a lot of people don't know Linux if they're playing around with this stuff, and they don't want to play around with running daemons in the command line and doing ifconfig with different devices to get them running. So that was one problem, and the other one was that there was limited support for Windows and OS X, meaning virtually no support. You could see the device, you could start the device up, and you could actually talk to it. The drivers worked, but that was about all. So in 2016, which is now, launched new software. And this is a graphical tool. It runs cross-platform, and it's meant to be sort of a basis to build more on top of that we can use to look at CAN buses, reverse engineer CAN buses, and also start to make some of these protocols available to everybody. So the hardware. This is an interesting one because last year I presented actually in, I think it was this room, about some Python utilities for CAN. And what happened was I had worked on this device, and the media sort of picked it up with just by chance, really. And everyone was writing articles about this, and I realized, okay, well, I better talk about it. But it was really never the focus of my talk, so there wasn't much about it. So I'll introduce it formally at Black Hat this year. And the hardware, it's a single-channel USB high-speed CAN device. So USB in one end, CAN in the other end, it gives you a network interface. It uses the virtual serial port USB profile, which, because it's over USB, actually allows you to do quite high-speed transfers. You can do 64-byte endpoint transfers and do it at speeds quite a bit higher than you'd expect with RS-232. And it uses this LAW ICEL protocol. I didn't make this up. This has been around for the RS-232 to CAN devices that have been available for quite a while. And the reason it uses this protocol is because Socket CAN supports it, so it's sort of become a standard. One feature it has that none of the other tools do, which annoyed me, so I decided to make it, is a jumper selectable pinout. The reason for this is everyone who makes official CAN tools seems to use pins 7 and 2 on the DB9 connector for CAN. These cables that use pins 7 and 2 cost like $70. If you use pins 3 and 5, you can buy these cables off of eBay for like $1 with shipping included. So it was really just I don't want to pay $70 for a cable every time, I'll make a jumper selectable pinout. And finally, it's open source hardware. You can go online, you can download the hardware, you can look at it, all the firmware is there, you can build it yourself, you can make contributions. There's been 2 forks of it actually. One is the Cannibal, which was done by actually a guy I met once, and he ended up deciding, hey, I want a CAN device that's smaller and has screw-down terminals instead of DB9, so he built a fork. Someone else did an isolated version, which was kind of neat, but that one is not really available. So there's a big picture in case you can't see it here. You can come take a look at it later, of course. And the schematic, it's really simple. Like, there's a microcontroller, some supporting lots of caps to filter it. There's an LDO for voltage conversion from 5 volts on USB down to 3.3. You have CAN transceiver, CAN high and low, jumper selection. There's a pinout for debugging. There's a jumper that you need to short out if you want to do a firmware update over USB. DB9 connector and USB. That's kind of all there is. Some test points, you're good to go. It's really nice when the whole schematic fits on one slide. And if you want to look at it in detail, of course, it's available online. So this is the new stuff, which is the CANtact software. And again, we kind of went through what's out there and why it was a bit of a challenge. The limitations right now, commercial stuff is expensive. It's Windows only, and you can't do too much with it unless you want to totally rewrite your own application using the APIs provided by the hardware manufacturers. So it limits you. Open source, it's all been Linux only, which, the open source guys love Linux, I don't blame them. It's been somewhat hard to use unless you're a Linux person, you're familiar with Linux. And graphical tools have been really limited. So there's Kayak, which is one that's been designed for this purpose. And that's Wireshark, of course. That's about all. And they're great tools if you're on Linux and you know how to use that stuff, but otherwise you're kind of stuck. So I kind of came up with some design goals for the software. I wanted it to be cross-platform, including OS X, because I happen to have a MacBook for whatever reason. Graphical, easy to use, easy to get started. You should be able to plug in, hit go, and see stuff. You should be able to do both the raw CAN, so signal database type messages, as well as implement diagnostics, because there hasn't been really much support for the diagnostics protocols in the open source world. Easy to extend. If you want to build a package for this or a module, it should be easy for you to drop it in. Hardware agnostic, so if you want to get one of these devices, that's cool. If you want it to run on a PCAN or a vector device, I haven't implemented that, but it should not be infeasible. It should be built in a way that it's easy to abstract the hardware out. And a focus on sort of reverse engineering, because that's what I've been doing a lot of. So tools that let you look at a CAN bus from the perspective of, hey, I want to do some reverse engineering. And that might sound, reverse engineering is this kind of scary term, but it's way simpler than you probably expect, and we'll take a look. So from that, there were some design choices that happened. Ended up going with Java, and the reason is if you want to do a cross-platform graphical tool, you don't have many other options that are good. Tried a lot of different things and settled on Java. It has direct device access, so instead of using something like Socket CAN, it's actually talking right to the hardware. And of course, it's open source, and you can mess around with it and make improvements or whatever you wish to do. So we're just going to go through the views of the tool. So you start it up. There's a config window to set up your device. You give it a bit rate. You give it the actual device name. hit go. These are the tools that will come up, and because I don't have kind of an automotive controller right here, the easiest way to show it is just to kind of demonstrate what comes out. So trace window, this is one of the simplest things you'll see in every single piece of CAN software. It's just going to show you all the messages on the bus. They're going to scroll by really fast. But you can record this, you can filter this, and take a look at what's going on. We did mention what's inside of a CAN frame, and I'll note that you have a timestamp. That's just when the hardware received the message. The ID is the second column. Data length code, third column, and the hex data, which is up to 8 bytes in the last column. So really that's all there is there. So it logs all the CAN frames by default. You can export it in the CAN dump format, which is the closest thing we have to a standard format for CAN logging in the open source world. There's a bunch of proprietary formats. Vector has their BLF format. Pcan has their own thing. CAN dump is quite nice, though, because you can take one of the dumps from this, save it as a text file, and then actually on Linux you can put it right back into this thing called CAN player, and it will replay the entire log. And you can actually use that with a virtual CAN device. So once you take a dump, you can just take that file, you can go totally offline into a lab and then replay it and take a look at all the information there. And it supports some simple filtering, so you can say, I want these ranges of IDs, and I just want to look at parts of the CAN bus. The live view is something that is very useful and very simple. Whenever you reverse engineer these CAN signal databases, really what you're looking to do is watch a bunch of messages all at once, change stuff, and see what actually changed in the bus. So we did GPS on a vehicle last week. We got in a car, we waited for a GPS fix, we drove it as north as we could, and we watched all the messages changing, and sure enough, you have something that's updating about once a second, which makes sense for GPS. And also, it's split into two 32-bit segments. And you have the first 32-bit segment, that's updating quite quickly, and the second one isn't changing much. So you look at it, and it was like, okay, we're driving this in this direction. This is latitude and longitude. That's how a lot of this happens. You kind of fiddle with the system, and you look at what's going on, and you get that information out. This live view, very simply, shows you one row per CAN ID. And what changes is the data. And as that data changes, and this is a simple example, it gets highlighted in red, which might be a little hard to see on this slide, but as you get a byte changing, that literally changes color. And what this lets you do is look at like 100 different CAN messages at once. You can see certain things changing. You do something to the system, be it, rev up the engine, stomp on the brakes, open the sunroof, change your position for GPS, and whatever's turning red is what's changing. It sounds like a really simple method of doing this. It sounds almost too simple when you explain it to people, but it works, and it works quite well. So it shows the newest data for a particular CAN ID. It highlights changing data, and it's useful for reverse engineering. There's some extensions of this that I want to work on. One is actually doing heat maps based on the rate of change of signals, because you have a lot of counters on the CAN bus that are just used as kind of for integrity, just to make sure you're not missing any messages. It might count from 00 to OF and then back to 00 and just keep going around. Those change at a very constant rate. You might not care about those at all, but if you get a heat map, you can just hit the brakes and watch what's changing at the rate you're hitting the brakes, and there's the brake signal. ISOTP. Now, I talked about diagnostics. There's a few parts of diagnostics. You have the CAN bus itself, and as we said, that only supports 8 bytes. But if you want to read something like a VIN number, which is around 20 characters, I forget the exact number actually, but there's about 20 ASCII characters, that won't fit into an 8-byte frame, so you need to chain some frames together in order to get that payload out. Now, what the ISO has standardized is this ISOTP, which is ISO Transfer Protocol. It's also called CANTP. It's sort of an interchangeable name. And it's just a standard for saying, I have up to 4,095 bytes I would like to send, and how do I get them into 8-byte CAN frames? It uses some kind of metadata on the frames in order to say this is the first frame, and we're going to send you this many, and send that payload. And there's serial number counter to make sure you're not dropping packets and it does all that at a lower level, but it's really useful to be able to do something where you just type in what bytes you would like to send that's longer than 8 bytes, and it sends it. So this window is solely for doing that. And you can enter a ID you would like to transmit on. In this case, we're doing 701. We want to receive on 702. Top is just what you're going to transmit. You hit send, and you get some data back. And this is actually doing this is in decimal, but it's doing a read data by identifier, I believe, of OX90 is 144. And it's coming back with hey, here's that data identifier. So this is actually doing unified diagnostic services, but manually. What this is useful for also is some manufacturers implement their own non-unified diagnostic services, standard services that you won't find in any standard anywhere. So you might need to actually be able to talk in individual bytes. So it supports this raw ISOTP format. It is the basis for automotive diagnostics, so it provides the ability to do these longer frames. But you need to know the standards in order to actually do anything. So that leads to the next tool, which is an actual diagnostics tool. This is showing a single view of it, but it basically has a UI for currently most of the common services and kind of working on building all of them in. So every single service, there's an ISO document you can buy. It tells you what the parameters are, what you need to send, what you will receive, and how to encode and decode that into the requests and responses. If you don't want to buy that document and then craft every payload yourself, you need some tool that will do it for you. This will do that. So for every service, you just select what service you'd like to run. In this case, we're doing security access. Security access takes these parameters. You have a security level. The default security level is OX01. There's a access record, which you can optionally provide. A lot of people don't use it for anything, but it is an option in the standard. You hit request seed. It's going to send that request for a seed, which is the first step of a security access. It figures out how to frame that, what data it has to put into the message, and sends that out. It gets you a response back with the seed. And then the next part of security access is you need to send a key. So based on the seed, you compute your key, and you hit send key, and it sends that over. And historically, as I said, the tools to do this were really it was a money thing, and it was either craft your own payloads, write your own software, or pay a bunch of money. So the goal of this is to make it easy. Scripting. So a lot of applications I find, okay, I need to develop this really quick and dirty script, and I don't want to set up devices and all this. I just want to do something really, really dumb and simple. So Java 8 introduced something called Nashorn, which is a JavaScript sort of just-in-time compiler for the JVM. It's really fast, which is nice. And this supports scripting in JavaScript. So you can load up a script, and it has some callbacks that get called when you receive a frame or whenever you get a ISOTP payload. And it also provides access to all of the functionality that is available to other parts of the application. So you can basically pull in the device and transmit raw frames, or you can pull in that UDS view that was back here and say, I want to do security access now. Here's the level, here's my data record, and it will do that automatically for you. It's useful for transmitting little proofs of concept. You can do things like a really simple denial of service, which is just an infinite loop that transmits CAN frames. You can log certain types of events. If you want to do some decoding yourself, you could say, when I receive a frame, it has ID OX123, I want to take the first 2 bytes, multiply them by this number, subtract something, whatever conversion you want to do, and print that out. It can be kind of useful for doing signal analysis. One example that I've used this for is security key extraction. So I had a diagnostic tool that somebody was nice enough to lend me, and it actually had the ability to do security access with airbag controllers, which are something that you want to be secure if you're driving around. And I thought, okay, well, this is nice. I have this tool, but I don't want to have to use this tool every time I access these devices because, the tool's kind of expensive. I need this laptop with Windows and this expensive software. So I could probably, dump the firmware from that, look at, do some or disassembly of it and figure out where they're storing these keys. That's one option. But a lot of the times these security access mechanisms, they're not very secure. So simple script that pretended to be a car. And whenever it received a request to send a seed, it would just start at 0, and it would just send the next consecutive value. So you get the seed of 0, 1, 2, 3, 4, 5, 6, 7. Keep going, and then whenever you got a response, it would print out what the valid key value is. Did this for about 10 different values, and then realized that it was just arithmetic. There was 2 bytes. The first byte you added a number. The second byte you subtracted a number, and that was the entire authentication mechanism. So, it took 10 minutes or 15 minutes to whip up a little script that pretended to be a car and did this, versus figuring out how to dump the firmware, getting the right tool, opening up and something like IDA and going through that. This seems just to be sometimes a more efficient means of doing it, especially when the tools are trusted. So that's kind of the current state of that software, but it is a work in progress. This is the first sort of public, hey, we have this tool, it's available. And now it's building more and more on top of it and figuring out what needs to happen next. So, signal decoding in database files. There's a lot of folks who are doing reverse engineering of CAN buses. A lot of them are sort of working in their own little worlds. Sometimes for commercial reasons, they do this work and they sell that information. But there's a lot of people who are doing it for fun, and the same stuff gets reverse engineered over and over and over and over again. Fortunately for us, the OEMs tend to use the same definitions for these messages across lots of vehicles for lots of years, and we can kind of work together to do some of these reverse engineering techniques. So Open Garages is one example of an organization that's trying to spread more information on this type of stuff. They also have a collection of, here's an Excel spreadsheet of signals we've found in this particular vehicle. There's no open, there is one open format, which is the CANtact format for defining all the messages on the bus. No one really uses that except for that CANtact tool. The traditional one is the DBC file from Vector. To be able to take in these types of formats or edit these formats and then do a live decode of everything on the bus is kind of a next logical step, especially as we're kind of working to make it easier to provide some of that information once you've done the research. Scripting improvements, so there's way more that the scripting can do, providing kind of common utilities for, hey, these are the problems or these are the applications I see come up over and over and over again. How can I just automate that and make it kind of sub-tool that will let you do that quickly and easily. Support for other protocols. So this entire talk has been about automotive. I'm sorry if you were expecting it to be about SCADA or about something else. But CAN is used a lot in SCADA systems. It's used a lot in motor control systems for industrial automation. They use protocols like CANopen, and there aren't too many good tools for working with CANopen other than proprietary stuff. And most of those are a pain too. I had one project I was working on where we had to do CANopen. It was not fun. We basically wrote our own tool was the solution. So to support those would also be useful for people doing different stuff with CAN that's not automotive. And performance enhancements. In the rush to get a lot of this stuff working, you sometimes forget about making it performant. There's some GUI improvements that rendering, batching rendering and things like that just make the tool a little less hard on your CPU. So that's one thing that I have to do some work on. And then there's the insert feature request here. It's open source. You can say, hey, we really want to be able to do whatever with this, and I'll at least think about it. And if you really want that feature in there, you can always write it yourself and submit a pull request for the tool, which would be awesome. On the hardware side, there's actually been a few people who, everything from like, hey, I don't like how the LED blinks. You should blink the LED this way. And I went, okay, I agree. So on the firmware side, there's actually a continuous integration server, so if someone submits it, I can immediately build it and test it really easily. Want to set up the same type of pipeline for this tool, so we can just test it, and if you're submitting features, it's really simple to say, okay, that's good, we're going to throw that in. Now, this was all about CAN and tools for CAN. It's worth kind of noting what's in the future, because, as I said at the beginning, we had a lot of years where no one touched CAN, and then it was assumed that CAN was secure because no one touched it and no one was going to touch it. That's not going to happen again. There's enough interest in this field that these emerging technologies, the research community is going to keep up with them. So here's some of the stuff that's coming out. You have MACD CAN, or message authentication on CAN. It's also called encrypted CAN, which is really a misnomer because it's not encrypted at all. And the way that works is you have your 8 bytes. This is how, there's a few different implementations. The typical one, 8 bytes. 1 byte is going to be a counter, 2 bytes is going to be a MAC, and now you have 5 bytes of payload. And that way you can actually, assuming you can get a key in all of these controllers, typically they're using AES CMAC, so it's AES-based means of doing that message authentication code. You can actually verify that this was from a real controller in the vehicle. Problems with this, well, a 1 byte counter for a message that's being sent at a rate of, let's say, 1 millisecond, you're going to exhaust that counter pretty fast, and if someone's logging these messages, they're going to be able to essentially do a replay attack as long as they can get the counter value and the payload value for a particular MAC. So it's arguable how useful that is to prevent against certain types of attacks. Other problems with this is you need to be able to do it quickly. I mean, these systems are real-time systems. If you introduce latency of doing verifications, that can totally destroy the system in some cases. There are real hard timing requirements. And if you don't get something in the right rate, often what cars will do is they'll go into an open loop control mode. I don't know if anyone's had a car go into limp home mode, but basically you can't get above 2,000 RPM. And if you're on the highway and that happens, it's kind of annoying. You basically put your foot to the floor and pull off the highway. Those types of things, they can't be happening on a day-to-day basis. So as you get more of these solutions, latency becomes a problem, and also the actual processor power to do this. Everyone wants to save money in the automotive field. Adding those types of features and the resources to do this, it's not free. It does cost money. So CANFD adds the ability to do 64 bytes of payload, and it also increases the bit rate from, I believe it's 1 megabit a second for normal CAN, and you can do 5 megabits a second on CANFD. It requires a different type of transceiver. It requires a different controller. You're starting to see these appear more in high-end microcontrollers, so it's not too available to the low-cost stuff yet. But with 64 bytes of payload, hey, you can toss longer counters and MACs in there. At least that's an option. And also you can reduce some of the overhead on the bus. There's other reasons that people are looking at it. And the last one that everyone seems to be talking about nowadays is automotive Ethernet. It's been in cars for a while, Ethernet. Just certain models have had Ethernet run around the car. Tesla were one of the earlier people to do it. But now we have this thing called IEEE 100 base-T1, which is a really sexy name for it. Broadar Reach was the more marketing name from Broadcom who developed it. What this is 100 base TX Ethernet over a single low-cost twisted pair. So with CAN, you basically twist 2 pieces of stranded wire together and you get a CAN bus. It's really, really cheap, and you can build it into existing harnesses. With Ethernet, you need shielding, and you need 4 pairs and all this stuff. So with this, you can take the wiring for CAN, and now you can do 100 megabits instead of 1 megabit, and you can do full-on Ethernet. So you can do UDP, TCP, anything you'd expect on Ethernet can be done over this. In order to work with a computer, you're going to need a media converter. So that actually converts this 2-wire Ethernet to your traditional 4-wire that you'd find, this computer doesn't have an Ethernet port, but most do. You can plug that right in. Those media converters are still quite expensive, so that's one new place where it's like, hey, that would be a useful thing to have, low-cost media converters. And also, we'll have to start looking at the protocols they use on Ethernet. So from sort of a high level, my thoughts on securing these vehicle networks, there's an argument you hear a lot in in this world where it's a physical access problem. If I have access to CAN, of course I can do whatever I want. I have access to the internals of the vehicle. And this is one reason that some of the more recent attacks that have relied on network connectivity, so things like with Fiat Chrysler, where they had the ability to do it over a 3G network, or attacks that are going to be going in over Bluetooth, short-range wireless. Even back in 2010, they had one via the OnStar system where you could call if you were on a phone call with them, there was a low data rate communication mechanism. So you could actually basically play a song in the car, and you would be able to issue commands in the CAN bus, which is really kooky, but amazing. So those types of attacks have really gotten a lot of attention, and for good reason. But I'd argue that the in-vehicle network, you also need to start looking at security. Because let's take a look at, IT as a parallel. This is like saying, well, we're going to have the world's most secure firewall securing our organization, but then within the organization, everything will be unencrypted, everyone's password will be password, and that's fine because we have this super secure device and no one could possibly hack it. It couldn't possibly be backdoored by the NSA. There's no way that anyone could get access to this thing. And anytime you've seen people make those assumptions, they've basically always been wrong. You need to have multiple tiers of security, and you need to understand that someone might get in the front door, and at that point, what do they have access to, and what do we care about them having access to? When you have these larger payloads, you have more options. Like I said, you can do bigger MACs, you can do encryption. The limitations are going to start to be the actual latency and the actual processing power required to do it. And the last part of this is, and what I'd like to leave you with, is that we have the growing attack surface. So most recent stuff, yes, we can turn on the windshield wipers, we can spray the windshield with fluid, we can disable the engine, which is pretty bad, sometimes even apply brakes at low speeds via the diagnostics stuff we were talking about. But as we go forward, you're seeing more and more autonomous features, where the integrity of sensor data is really important because it's deciding where to steer that car or whether it should apply brakes or not. So the damage potential is going up. It's kind of hard to argue that that's true. At the same time, you're seeing more and more convenience features come in and more connectivity. So whether it is simply you have an app on your phone that lets you turn on the air conditioning in your Nissan Leaf, or you have the ability to open up an app on your phone and have your car valet itself autonomously up to your door and you hop in. Those types of features, they require connectivity. And they require access all the way from a mobile device down to driving the car. So damage potential is going up, and attack surface is going up at the same time. Basically, it's not a problem that's going to get simpler. It's one that's actually going to get more and more complex. So it's an interesting thing to be looking at. I think we've only sort of scratched the surface of what's coming, and it's going to start being something that if we don't look into now, you're going to end up down the road with vehicles that have all sorts of amazing features, but create huge amounts of risks that won't be acceptable. And so that's kind of my prepared content here. We can move to some questions and just some links here I'll explain. GitHub.com/linklayer has all of the hardware, design, firmware, software tools you can download there. It's all on that link. I will also get this talk up on, I'll try to get it up on there. CANtact.io is the website for these devices. You can get them there. At Eric Evenchick is me if you like the Twittery thing. If you like the email thing, then that's the email. You can come say hi. And I'll also be around here. They've let me open for the fantastic Michael Osman, so I'll be around here for his talk, and then I'll just kind of be floating around. But yeah, stick around for radio reverse engineering, and we'll move to some questions for me. Thank you. Anyone? I know it's early. This is going to be too easy if I don't have any. Yes.
Is there any way to know if someone has been doing something with this tampering the data or changing the data or modifying the mileage or whatever?
Yes, so there's definitely some research going into intrusion detection for these types of networks. The really naive way of doing that is because we have these signal databases that define everything that should be sent, the valid ranges for all of those signals that should be sent, the rates at which they should be sent. You can sort of do some basic heuristics to say, oh, well, this message is being sent too fast or with out of range values, and use that to determine that some breach is happening. But one really big problem is actually what you do if you detect these problems. So if you detect that some attacker is on the CAN bus, what is the next step? Do you shut the car down? Well, that is not really acceptable by any OEM. They never want to shut the car off. I mean, you look at key fobs today, you can do a range extension attack on some vehicles. You can do a range extension attack, jump in, start the car, and you can drive it forever until it runs out of gas. Because they don't want to shut down the car just because the key was lost. That could be, if it happens to shut down on a railroad track, that could be really bad. So, yeah, there is some research being done into intrusion detection, but another big problem is, what is your mitigation step once you actually find an attacker's there? Yes?
Can you give some examples about the scripting ability?
Yeah, so I mean, my favorite example of scripting is the silly one of doing a denial of service. I didn't talk about the electrical characteristics of CAN, but really simply, low IDs have priority and they win. So if you send the message with ID 0 really, really fast, you will basically shut down most cars. That's one really fun one that is like 3 lines of code. Other things, it is really useful to be able to do just really fast decoding. So I just want to spit out these bytes in this format. It's kind of hard to write a tool that is generic enough to meet all the requirements. So if you can write 5 lines of JavaScript that pull that out and do like a printf with the right, the way you want to see it, you can do that. And then you can also just save the log, which is really convenient. And then other things are pretending to be a vehicle for the purposes of reverse engineering diagnostics tools. So I use the example here of, send a seed, which you've chosen. It's really a chosen plain text attack in this case. You're choosing what you want to have them encrypt. And they'll send back that valid key. That's one example, but other ones include, if I have a diagnostic tool and it has this really cool routine like apply brakes, which a lot of them do for the purpose of bleeding brakes, I can pretend to be the car and say, okay, when I get a request for that routine, I'm just going to send back, I'm happy, I'll run the routine. Then you just take your diagnostic tool and you start punching all the buttons on it, and it comes up with what every routine code is. That's proprietary information that typically you wouldn't be able to get from a manufacturer unless you pay them the $50,000 royalty for most of them that they're asking. You can really quickly write a script. It's like 10 lines of JavaScript or something to do that type of thing. Yes?
Eric, so it's known that Bosch like to stop you from tampering with the hardware, so encasing a lot of their relays and stuff in resin. Do you foresee manufacturers doing this with the CAN bus in the future?
In some ways, hopefully. There are physical attacks that there is history of them, that you can be outside of the car and get on CAN because you kind of smash a tail light or you get onto the power steering pump or something like that. These are not physically in the car. And then from there, you have access to a CAN bus. And like we said, it's just a big bus. There's no switch. In a lot of cases, you can't identify where traffic's coming from. So physical security will definitely be part of it. Of course, someone can always smash the window of a car. That's an assumption you kind of have to make. I like to say that the oldest denial of service attack on cars is slashing the tires. That it's pretty effective. But physical security, at least for CAN, is going to start to matter when you see the risks for it. In terms of the devices themselves, you can pot them, you can do all sorts of things, but don't assume that no one can remove it, because every time that assumption is made, it's proven wrong. And there are hundreds of examples of devices that said, oh, well, no one will be able to get inside of our device. And it turns out with enough time and enough hot air guns, you can remove most potting. So, right. So I have about 5 minutes, but if there's no more questions, I'm happy to take whatever you come up with later if you want to ask things offline. But just the last thing is thank you very much for coming out to this, especially at 9 in the morning. You're great. And also thanks to the folks at Black Hat for having me again. It's always great to come out to these events and present stuff. Hopefully you found it useful, and hope to see you at one of these types of events in the future. So thanks.